Hi, it's Bruce, and welcome once again to my Colorado Rocky Mountain Labs. For the last several years, and as you'll know this if you've watched any of my videos where I've used this scope, but this BK1590A has been my scope of choice on my bench. I use it regularly. It's the first one I go to, and I do have other scopes. I mean, I've got a nice Tektronix, two of them actually, a 300 megahertz and a 400. But I prefer generally to go and use my 100 megahertz B&K. It's got all the features I want. It's been trustworthy. It's ergonomically just easy to use. Kind of everything is intuitive on it. I really enjoy that unit. So it's been my favorite. So today, I'm happy to say that I have an identical B&K 1590A that I'm going to be offering on eBay, and we're going to take you through its operation and testing. Show you what we got. Very clean unit, very nice looking. Very little in the way of any kind of scratch or mar. There is a little mar right here and here, but for the most part, it's in pristine shape. We are missing a little plastic cover on the handle at this point. Doesn't affect the operation of the handle. Um, would look like this if we had it, but we never received it. So right now, I'm displaying four traces, four independent traces. The upper and lower are square waves that are on channels 3 and 4, and the middle two traces sine wave on channel 1 and 2. It is a four um, trace scope. Channels 3 and 4 are limited to two vertical ranges. You have zero point 0.1 volt per division, or you can go to 1 volt per division. So you can display up to 8 volts on the screen, and probably the smallest usable voltage would be about 0.1 or maybe 0.05, something like that. Uh, Channel 1 and 2, you've got a vertical volt per division range switch on each one, capable of going from 5 millivolts per division all the way up to 5 volts per division. So you'll be able to display about 40 volts on the screen without using a divider in your scope probe. But if you go to divide by 10, then you can do up to 400 volts. Um, it is conservatively rated at 100 megahertz. This one will be tested to be on that. Um, it is loaded with features. Like, for instance, you can pull on a vertical gain of times 5 on either A or B. You can change the horizontal gain to times 10. Make that a little more visible. You can invert channel 2. That's non-inverted. There's inverted. We have a 20 megahertz bandwidth limitation, so we can eliminate any noise that's outside of the first 20 megahertz that you maybe want to work within. That's nice for eliminating a lot of hash. Um, let's see, we have dual mode, channel 1, channel 2, dual, additive mode, quad mode, and right now we're in chop, and here's alternating. So you have two different kinds of display. Let's go ahead and go back to quad. We have a beam finder. We've got an excellent focus. Very sharp display. Plenty of brightness. And we can do AC, ground, DC on all of the channels. We can change, oops. You'll notice that my square wave on the bottom has diminished greatly. That's because I divided it by a factor of 10. Okay. Eliminate some of that hopping around. We have two different sweep rates available on this. We got the A sweep and the B sweep. The A sweep is just like on every other scope. The B sweep is only found on some scopes, and what it does is it allows you to sweep at a faster rate and expand a section of what is on display. The benefit to that, let's see, if we were to go to there, you can see channel 2. I've changed the sweep on B while I've maintained the sweep on A. Here we're in the A intensified B, where we get the signal on A, and then we can change the time delay on B to take a look at a portion of A. And the part of A that isn't the B is dim, and the B section is bright. And then we can take a look at B separately by hitting alternate. And now B is down below. So we can see that we've expanded 1, 2, 3, 4 peaks. 1, 2, 3, 4. We've expanded those peaks by increasing the time of sweep on the B channel, which is the center knob here. So as I'm increasing my speed, you can see I can only display less and less of the peaks of A. So here I'm displaying only about 3/4 of a cycle of A expanded down below. So it's really handy if you need to take a look at a section of a complex waveform and you want to expand it and look at it. I've done this on other videos where I took a look at the television signal, the NTSC signal that goes through a television, and then I've expanded sections where you could look at the stair step and so on for retrace, and you could see the color section and so on. And then beyond that, like I said, we have the times 10 magnification. We can change our horizontal position. We can change the source from channel 1 to channel 2, and then you've got all of the accompanying trigger modes. We got auto, normal, single, and a reset for the trigger modes. The extra 2 inputs down below. And then we have the 1 volt peak to peak 1 kilohertz probe adjustment signal. So you've got everything here, and it's in a beautiful layout, very easy to master. And we're just going to take a look at testing this unit a little bit. Okay, so we've opened or removed the insides of the 1590A so that we can service, calibrate, clean the unit. I just got through cleaning the attenuators for the volts per division vertical, and just figured since it was open I'd give you a look at the insides of this thing. It's impressive. Combination of digital and transistors. The far side here is a little dark on this side, but used to be the horizontal side. Time base. Very neatly designed and built, and I've had very little problems with the one on my bench, which my favorite unit right there. Okay, let's keep going. Okay, well, I finished the calibration, put the unit back in the cabinet, and I've turned off the overhead lights so we can kind of more easily see what's going on the screen. I'm hoping that I have this adjusted so that it's not overpowering, but yet easy to see. So right now, what do we have here? We are looking at the screen, and according to my horizontal sweep time, I'm set on 0.1 milliseconds per division, but I can count 10 divisions across the screen from left to right. So 10 divisions times 0.1 millisecond per division would be 1 millisecond. So this waveform that I have completes a complete cycle in 1 millisecond. Anything that completes a cycle in 1 millisecond has a frequency of 1,000 hertz. Now what else do we see? Well, right now we are reading on channel 1 0.5 divisions vertical, 0.5 volts per division vertical. So 1, 2, 3, 4 divisions vertical times 0.5 would be 2 volts. So I'm going from a negative 2 volts up to a positive 2 volts, or 4 volts peak to peak. That's interesting. So let's take a look at what's generating that signal. So we follow the line back. And here's the line. Okay. Right now, this digital signal generator is giving me an amplitude of 4 volts peak to peak and a frequency of 1 kilohertz. Well, that's exactly what I measured. So that's working beautifully. And that was on what, channel 1? Oh, wait a minute. Wait a minute. We're connected up so that both channels are in parallel. So does that mean that I have 2 signals up there? Well, let's turn off channel 1. We'll ground it. And there's channel 2. Huh. So putting channel 1 back on again, it just overlays. If I turn channel 2 off, and I make channel 1 the source for the trigger, then we freeze the screen again, and we see that we have a signal on channel 1, and if I put channel 2 back on, we got a signal on channel 2. It's the same signal. And because we're calibrated, it looks like one trace. So, kind of showing off a little bit here. The unit's in nice shape. It's in good cal. And, well, that's really all I've got to say about that. We'll take a look at a few of the features. All right, we've got another signal on here. Let's take a look at it. Right now, the signal's coming in on channel 1. We're at 0.5 volts per division. We go up roughly 1, 2, and nearly a half divisions. So 2.5 times 0.5 would be 12. That'd be 1.2 volts. And then peak to peak, 1.2 volts times 2 would be 2.4 peak to peak. Then, frequency-wise, I am about 1, 2, 3, 4, 5 divisions in one cycle. And right now, I am at my fastest horizontal display rate. That's 20 nanoseconds per division. Times 5 divisions would be 100 nanoseconds or 0.1 microseconds. Well, anything with a period of 0.1 microseconds would be running 10 megahertz. However, I have pulled out my times 10 magnification display. So if it's 10 megahertz, then times 10 horizontally would be 100 megahertz. So I am looking apparently at 100 megahertz with a 2.4 volt peak-to-peak display. Now if I push in on my times 10, we see that we are now displaying 10 times as many peaks as we did a minute ago. And all of our calculations would be reduced by a tenth. But in any case, this is a 100 megahertz displayed on this screen right now, and it's a 100 megahertz scope. So that's what I wanted to show you. Okay, so here we have all 4 channels demonstrated on this unit. Both the top and bottom traces. This would be channel 3, channel 4. Here's channel 1 and channel 2. Channel 3 and 4 are it's a sine wave, 1 kilohertz, 0.1 volt per division. And so that's the upper and the lower. And then the in-between is a triangle wave at 2 kilohertz at 0.5 volts per division. And we have control over the channel 1 and 2 as far as the vertical gain goes. We can do that. We're limited to 2 ranges. We can divide channel 3 and 4 by 10. Right there, that's by 10, or back to 1. So it'd be a useful thing if you wanted to look at, say, 4 outputs on an IC at the same time, or 4 outputs anywhere at the same time. Could be done. Just have to be, well, 1, 2, 3, 4 divisions up or down. If we were in the 1 volt per division range, we could handle up to 8 volts on channel 3 and 4. And we could handle down to as little as, say, 0.1 volt. You'd be within 1 division in 3 and 4. So that's your restriction. Channel 1 and 2, you can adjust the vertical gain to go right down to from anywhere from 5 millivolts per division up to 5 volts a division. So you've got pretty good range there. But I've seen few scopes that do this, and this one does. Okay, right now we are on the AC signal input mode. We're on 0.1 volts per division on channel 1. We have a display right now that we are going to adjust the centering on a little bit. It's using this little knob over here. Okay, I adjusted it so now that I'm crossing on this edge and this edge. And I see that I have 1 full cycle, and that's in 10 divisions. And I'm working at a speed right now on the sweep time knob of 10 microseconds per division. So I've got 10 divisions, 10 microseconds per division. That's 100 microseconds. Yeah, if it was 100 microseconds in period, then that's 100 times slower than 1 megacycle. And so 10 times slower would be 100 kilohertz, and 100 times slower would be 10 kilohertz. So we're looking at a 10 kilohertz signal. And right now I am dialed in to 10 kilohertz on my my frequency signal generator. And I'm also at 0.6 volts. I know that that's true too. So I'm at 0.1 volts per division, and I see 1, 2, 3, 4, 5, 6 divisions. So I am at 0.6 volts peak to peak on the display. And it's looking very good. Let's try channel 2. And then we change our source to 2. Just touch our, there we go. So once again, we're looking at one full cycle in 100 microseconds, so 10 kilohertz again. The horizontal, it's the same horizontal display, so that shouldn't change at all just because I changed the vertical or the channel. And we are looking at 1, 2, 3, 4, 5, 6 divisions. And again, we're at 0.6 volts peak to peak, so that's looking really good. Let us go ahead and try 0.2 volts peak to peak, and we'll change our setting over here. That's 0.4. Yeah, let's go make it 8. Okay, there's 0.8 volts. So we're 0.2 volts per division. There's 0.2, 0.4, 0.6, 0.8. No problem. Same thing would be true on 1. .8. 0.5 volts per division, and we change to, right now we are at 4 volts. So I'm looking at 1, 2, 3, 4, 5, 6, 7, 8 divisions times 0.5 volts per division on the vertical. That'd be 4 volts. And we have 4 volts displayed. Changing to channel 2. And switching to channel 2 there and putting our gain at the same source as channel 2 for the triggering, and there we go. There's 8 volts. We're going from the bottom of the screen to the top of the screen, and again it's in 0.5 volts per division, so that looks good. If we change to 1 volt, then we reduce ourselves to half of the screen. Down 2, up 2, that's 4 volts at 1 volt per division. At 2 volts per division, we go down 1 and up 1. That's good. And let's go ahead and change ourselves to 5 volts. And then let's change to 5 volts per division. And we should be able to see that we are... I'm going to go ahead and move this down so that we are on the line. And there we see we do 1 division. No problem. Here's 5 volts per division. We get 1, 2, 3 divisions, 15 volts. I just changed my amplitude to 15 volts on the generator, so no problem there. Let's take a look at channel 1. We're going to go to 5 volts per division, hit channel 1, change our trigger source to channel 1, and let's adjust the bottom of the trace so that it's right on the line. There's 1, 2, 3. 3 divisions, 5 volts per division, 15 volts, no problem. And again, we're at 10 kilohertz, everything looks great. So we're getting really good readings out of this thing, both in frequency and in voltage. Let's try and crank our frequency up. We'll go to, say, let's do 20 megahertz. Okay. All right, we are right now at 1 volt per division, we're going to check our, we're going to center ourselves here. Okay. And I just dialed in 4 volts on the generator over here. And what I've got now displayed is up to, down to, at 1 volt per division, that's 4 volts. We are going to adjust so that we get one cycle starting right in the middle of the screen. I'm just adjusting the little horizontal movement here. And there we begin our trace right in the middle of the screen. Come up, come down, and come over. We do that in 1 1/2 divisions. I'm sorry. 1, 2.5. It's 1, 2, and 1/2 divisions. Okay, and I'm set right now to 20 nanoseconds per division. So we are going 2.5 times 20. That'd be 50 nanoseconds for a cycle. So you're doing one cycle in 50 nanoseconds, and you do 1 over that amount, and you're going to wind up with 20 megahertz right in the nose. All right, right now we're taking a look at a 1 megahertz signal. We've got the signal amplification set so that we are at 0.5 volts per division. We're up 4, down 4. So that would be about 4 volts peak to peak. And if we now turn our frequency up to 100 megahertz, and we take a look at the output, as long as we don't fall to less than 2.8 divisions, 1, 2, we are right now at 3.2. So we've exceeded the 100 megahertz 3 dB point. You know, yes, we've gone, we went from 4 divisions down to 3.2 divisions, but until we hit 2.8, we haven't hit the 3 dB mark, which is the limit of the bandwidth. So let's go ahead and increase our frequency to see where that would be. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so it's more than 9, so we'll go 10, 11, 12, 13, 14. I'm going to call it 14. So it looks like 114 megahertz bandwidth, and we get 3 dB on the screen. So we've got the bandwidth, we've got the frequency, we can increase our horizontal time by a factor of 10 and get a better look at the waveform. That's 114 megahertz. So there you go. Not much else. I mean, there's a stigmatism control, there's a trace rotation to move the trace, flatten it out. All of that's been adjusted. There's really no need to fool with it. All right, so now we have a 1 megacycle signal on channel 1. We've got another 1 megacycle signal on channel 2. Let's pop ourselves into the XY mode. In an XY mode, we see the Lissajous pattern that shows an ellipse very slowly revolving. Revolution has to do with the difference in the frequency between my two signal sources. So my little K-Moon signal generator versus my PTS 500 up here. PTS 500 is putting out a 1 megahertz signal, but it's being driven by a rubidium calibrated master oscillator. So I trust the frequency coming out of that a lot more than I do the frequency coming out of this one. And what I'm seeing here is that I'm approximately 4.3 cycles out of a million different between the two signals. If I was to drop that, like I said, 4.3, here's 4.2, 1, 0. And if I go to the 4, there's 3, 2, 1. So there's 1 megahertz between the two of them, and we see that we're rather quickly oscillating. It's about 4.3 cycles it's doing a second there. So I could look to see inside this unit whether or not I have a calibration for my frequency, and if I do, I could adjust it, but for all intents and purposes, it's great. But I wanted to demonstrate the XY mode as well, and it's working. So let's, there we go. You know, just for kicks, I went ahead and connected up my PTS through a coupler into my the counter section of my signal generator counter here. And I'm reading the frequency that the K-Moon says my PTS 500 is coming out at. And it's varying between 1 megahertz plus 4 or 5 hertz. It varies. It goes from 4 to 5, which figures because I said it was like 4.3 hertz off. So I believe I would need to increase the frequency of my counter's master clock in here by 4.3 hertz to eliminate that error. Just for curiosity. Well, I appreciate you listening to me and reviewing my scope. And again, I'll let you know that with the scope, you'll receive 200 megahertz probes and a set of manuals. You'll have the user guide, the calibration guide, the parts list, and in addition, there will be a information service book for the Kenwood 2100, which it's identical. It is the same unit. I believe Kenwood made this unit for B&K Precision. It's great information, has all of the same circuitry and everything. However, I will let you know that you cannot utilize the schematics as far as the call-out numbers for the pots and resistors and things like that, because they did change them when they made this unit for B&K. But like I said, it's great reference information if you need to identify what's going wrong on something someday. Then you'll have the information to read about, and then you can reflect back to the B&K information, which will help you repair or do calibration or whatever to this unit. So you'll have all of the information I can give you, and you'll be all set. I think you'll love this oscilloscope. I do. 100 megahertz is a good range as well. I seldom venture outside of the 100, even though my bench is set up to do so. I think probably most of you are going to find that you're dealing with less than 100 megahertz on the bench anyway. Those that aren't, you're going to need to buy more expensive equipment. Well, once again, thanks for listening. Happy bidding.